Laura Shackelford, thanks so much for coming on to Evolution Soup all the way from your office in Illinois. You are a professor in the Department of Anthropology and the anatomy director for the Carle, Illinois College of Medicine. Your research focuses on the evolution of Homo sapiens as a way of understanding recent human diversity. In 2018, your team unearthed fossils in a cave in Laos, Southeast Asia, fossils that surprised everyone when they turned out to belong to the mysterious Denisovan hominids. So how are you doing, Laura? I know that you're between semesters at the moment, so other than doing the occasional interview like this one, what else have you been up to?
Yeah, thank you for having me. This is a break for me. I'm between semesters, but I also teach in the medical schools, and this class is year-round, so it's only a little bit of a break. But while I do have some time, I'm doing some research, which for me mostly means doing some gaming and some game development.
Before we explore the enigmatic world of the Denisovans, let's just hear a little bit about your background. Laura, did you always have an interest in science, and in particular, human origins?
Well, I didn't grow up thinking about dinosaurs or wanting to be Indiana Jones or anything like that. I didn't really learn about anthropology or the idea of human evolution until I was in college. I'm from a relatively small town in the South, and evolution just wasn't part of our curriculum. It just wasn't mentioned, except for maybe the rare occasions when a teacher would introduce it with, "Now, I don't believe in this, but as a teacher, I have to tell you about it." So when I did finally encounter it in college, it was this fantastic unifying theory that made lots of other things make sense. But I really came to love fossils and human fossils in particular because of what you could learn from bones and the idea that there was so much potentially useful information in the skeleton just waiting to be figured out if you knew what questions to ask and if you knew what to look for. And then when you add field work where you get to keep playing in the dirt, then I was hooked.
The Denisovans were made known to the world in 2010 and was an extremely interesting find in more ways than one because, like so many discoveries, they were found when no one was really looking for them. Isn't that right?
Yeah, so that's exactly right. We weren't aware that they even existed until, like you said, about 15 years ago. And there are only a handful of fragmentary fossils from this group, and some of these have produced DNA. So the majority of what we know about them, we've learned sort of indirectly from their genetic legacy in populations that are living today. So I guess sort of the short answer is that Denisovans are the Asian version of Neanderthals. They're an extinct sister taxa of the Neanderthals that are known from just this handful of fossils. In about 2008, there was a finger bone that was excavated from Denisova cave in the Altai Mountains in Siberia. And scientists sequenced the genome from this bone, and they found that it really wasn't a perfect match for modern humans, and it wasn't a perfect match for Neanderthals. And instead, it came from a previously unknown group that was really closely related to the Neanderthals, but that split from modern humans about 700,000 or 800,000 years ago. So again, we can kind of think about them as the Asian version of Neanderthals. And after splitting from modern humans, the Neanderthals and Denisovans diverged, with the Neanderthals occupying Europe and the Near East, and then the Denisovans having sort of a wide geographic range in Eastern Asia. And based on the genomic sequences of people that are alive today, we know that the Denisovans also contributed to the gene pool of living people. So in fact, we know that people living in island Southeast Asia and Oceania and Pacific Islands have as much as 5% of their genome from the Denisovans. So as of now, we have 4 fossils that are from Denisova cave. Then we have a partial jaw from the Tibetan Plateau, and then we are adding this tooth from Laos. Now the problem, or one of the problems, is that we don't know what they look like. This is the only fossil species or hominin species for whom we know more from genetic data than we do skeletal information. So we don't know what they look like, and this creates a real problem for fossil hunting, and also for understanding their spatial and their temporal range, as well as their relationships to recent populations. There's a good chance that they may already be represented in the fossil record. For example, in Chinese fossils, or just in some of the fossils that we have previously called maybe Middle Pleistocene Homo from Asia. But we just haven't known previously that we should put them into the same category with what we're now calling the Denisovans.
Right, and it was interesting way back when it was found. It was Svante Pabo, I believe it was, from the Max Planck Institute in Leipzig. He expected to find Neanderthals, and it was a huge surprise when one of the researchers came to him and said, "We don't know what this is."
Yeah, I wondered, like, was that a disappointment to not find a Neanderthal when you're looking for one? I can't imagine that it was, but it is strange to not be looking for this population and then to find something that's just not it's not anything that you anticipate. It's not a Neanderthal, it's not a modern human. So what in the world can it be? So that must have been a really exciting moment to be able to identify something that was absolutely real and absolutely existing, not only living sort of alongside Neanderthals and alongside modern humans, but actually interbreeding with modern humans. So I imagine that was a pretty exciting moment.
Okay, let's get into your team's amazing find in 2018. You were excavating a cave in Laos, Southeast Asia, looking for and expecting to find early modern humans, and some of them were exactly that, but others definitely were not. So tell us about this discovery.
So I've been working in Laos for a long time now. I've been working there with primarily a French team, a French and Lao team since 2008. And we've really been looking for modern human fossils. And we've been pretty successful there looking for some early modern human fossils at sites like Tampaling. But it's a really extensive limestone cave system where we're working. This is in the Annamite Mountains that run along the border of Laos and Vietnam. And so it's a very extensive system of caves and rock shelters and sinkholes and lots of places where you can potentially find fossils. And what we've been doing over the last 10 plus years is actually excavating inside many caves and digging in the dirt and going through the wet clay that we find in the caves there. And at places like Tampaling, we've found some early modern humans. But this site, Cobra Cave, where we actually found the Denisovan tooth, is quite different because it's a breccia site. So it's not somewhere where you dig. So every year when we are in Laos, while we excavate, we have geologists and a couple of professional cavers that we have started sending out throughout the area just to look for potential sites. And there are just so many that could be fossil bearing. And so they go out, they look for potential sites. And in 2018, there were some sites they're all nearby. All of the sites we've excavated are within about 500 or 1,000 meters of one another. We still haven't made it off the first mountain that we started on because there are just too many sites to excavate. It was lunchtime, and most of us were gathered for lunch, and we were waiting for the geologists to come back, and we were hungry and we wanted them to hurry. And so they come back, and when they come back with their pockets full of rocks. They came back with their pockets full of breccia. And so they tell us that they have found this cave.
And what is breccia for people who don't know? It's like concrete, isn't it?
It is. It's a lot like concrete. So it's a really solid matrix that is like concrete. And so when you excavate it, rather than being on the ground excavating like you normally would, this is usually found on the walls and the ceilings of caves. And in order to excavate it, you really have to take a hammer and chisel to it or something like that. And you chip it off of the cave walls or the cave ceiling. So this is what they had done. They'd found this breccia, and in the breccia, sort of just scattered throughout it, like fruit in a fruitcake, were all kinds of teeth, and they were mostly animal teeth. So as the geologists come back to the site for lunch, they start to pull out these rocks, these breccia pieces from their pockets, and every one that they pull out just has tons of teeth in it. They're animal teeth, and so we're looking at these teeth and sometimes little bits of bone, and then they pull one out, and there's a tooth that's different, and it's not an animal tooth. We absolutely know that it's a hominin tooth because our teeth are really distinctive, and so it was super exciting. And of course, we were no longer angry that they were late to lunch, and we started to take a look at this tooth. Now it's really hard, you have to chip away at the breccia. Sometimes we even use a weak acid to remove it from around the bones. So just to give you an idea of sort of the difficulty of getting things out of this matrix. But we start to chip away at the breccia and remove this tooth. And as we do, we start to realize that, yeah, it definitely is hominin, but it's not a modern human. And so our first assumption was, of course, that it was probably a Homo erectus. Not because we thought we were going to find a Homo erectus, but because Homo erectus has been found in that general area previously, sort of in that larger geographic area. And so as we continued to look at it, both in the field and then as we took it back to our hotel that night, we started to realize that it wasn't really right for a Homo erectus either. And so I'm really lucky to work with Fabrice Demeter, and then we also had Clément Zanoli in the field with us, and both of those guys are fantastic experts with dentition, with teeth. And they were not only able to take a good look at the tooth, but also to compare it to some micro CT scans that were available. And when we really started to look at the tooth and started to compare it to to the available scans that we had, we realized that no, it wasn't Homo erectus. In fact, the only thing that this tooth resembled, the only possibility that it really could be, was a Denisovan.
Wow. And I think I'm right in saying, Laura, that the reason we find a lot of teeth is because they're such a hard material compared to the rest of the skeleton. Obviously, they're needed for chewing, that they preserve better.
Yeah, that's exactly right. Ultimately, all of these bones and teeth they're getting moved by water, and so as they get moved by water, they get rolled on riverbeds and on rocks, and so lots of the bones break up, and there's a much greater tendency for the teeth, which are much harder to preserve, as opposed to the bones, which will break into pieces and not be preserved as frequently. And so, yeah, it's a lot more likely that we're going to find teeth in this breccia than that we'll find bone. And we find a little bit of bone, but it's generally just small pieces that are just fragments, and they're hard to identify as to what they are or who they come from. But the teeth are nice and distinctive. So there were a lot of things that we needed to learn about this tooth. And the first thing that we kind of were able to determine about it, other than, it is likely a Denisovan, was that it came from a child. And this we could tell, again, this was something that we could tell right away because it didn't have a complete root. So, a tooth has a crown that we see in our mouth, and then it has a root that's still in the gum. And so this tooth didn't have a complete root. It hadn't grown yet. And so that means that it was still in the gum when this child died. And so it hadn't erupted out of the gum, and so it hadn't had a chance to do any work. The enamel hadn't been used at all. It hadn't been crunching on anything. And so this was the tooth of a child. Once we got it back into the lab and were able to look at some other things, one of the things that we did was we extracted proteomes. And so we didn't extract DNA from this tooth, but we extracted proteomes, which are sort of a product of DNA. And so what these told us was that it was definitely hominin. We knew that it was definitely from either a modern human or a Neanderthal or a Denisovan. So we were, that we didn't really narrow things down very much, but at least we were in the right ballpark. And it told us that it was a girl. So we were able to determine that this was a little girl who died probably when she was about somewhere between 4 and 6, maybe 7. And those were sort of the first things that we were able to really determine about this tooth.
And what does this mean for the Denisovan puzzle overall, do you think?
Yeah, so one of the things that was most amazing about this is, once again, we weren't looking for Denisovans, in large part because we haven't really found them in very many places. Until just a few years ago, they'd only been found in Siberia at the original site of the Denisova cave. And only a few years ago, another partial jaw was found on the Tibetan plateau. And that was really interesting and really exciting. But it also it expanded the geographic range from which we knew Denisovans existed, but it was still sort of this cold environment. And in the case of the Tibetan plateau, this hypoxic environment. So based on the DNA of living people, of people who are alive today, we know that at one time Denisovans had a very broad geographic range. They probably lived, across a broad range of Eastern Asia and down into the islands of Southeast Asia and Oceania. So we have known that, but we haven't had any real evidence that they existed there. We even know that it's likely that they ran into modern humans and sort of interbred with them somewhere, in that, on the possibly mainland Southeast Asia, but in that general area of the world. And so when we found this tooth, it was really great evidence that that what we had previously thought about their geographic range was in fact true. So previously we had known that the Denisovans most likely lived in this large geographic area, but now we had some proof. We had some tangible evidence that in fact Denisovans were here. And it was also really interesting because now it wasn't just, we weren't just finding Denisovans in a cold environment, because at the time that Denisovans were living in Southeast Asia, so at the time that we found them here, it would have been a very temperate environment. And so not only did we kind of find some tangible evidence that Denisovans were where we thought they were, we also were able to determine that Denisovans were adaptable. They weren't just living in cold environments. In fact, they were able to adapt to the cold, to the hypoxic environment of the Tibetan plateau, but they also were adapting to some temperate and tropical environments. And so they really had that adaptability that we think of when we think of modern humans. A little less so when we think of Neanderthals, but Denisovans were, we could now say they were living in this wide ecological range as well as geographic range.
It's a shame we can't put together a proper sort of skull, a face to these people. Not really, not yet.
It is a shame, and I think that I and lots of other people think that maybe we can. That it's likely that we already have Denisovans represented in the fossil record. We just haven't known what to call them, and so it's possible that we have looked Denisovans in the face. We just didn't know it at the time.
There might be something in a drawer somewhere in a museum. It'll be reclassified. Right.
Yeah.
People following this discovery may also be aware of evidence pointing to a so-called ghost population, that is, another mysterious hominid group that lived in Southeast Asia and interacted with the Denisovans. So what can you tell us about these people?
So ghost populations are groups for which there are no descendant groups, or and for which there's no fossil evidence. And so instead there are some features of the genomes from either archaic or usually modern living humans that are best explained by statistical models that include introgression with these ghosts or these as yet unidentified groups. So presumably there is an unknown ancestor that diverged from the lineage that led to Neanderthals and Denisovans and present-day humans. And that population is the one that we are referring to in this particular scenario as a ghost population. Excuse me. Now, we could also think, just sort of to give you a better idea of a ghost population, before the Denisovans were named, we could think of those Denisovans as a ghost population, because when their DNA was first identified, it didn't belong to a group that already existed. It belonged sort of to an unknown group. But then this population was quickly identified as this sort of new group known as Denisovans, even though they don't have a sort of a new taxonomic status. But now we know them as Denisovans. It's just that there were probably similar groups in the more distant past that were similar in that they existed, they contributed some of their DNA to populations that come later, including modern human populations that still exist today. Now, what's interesting is that we have fossils now for which there's no genetic data available. So obviously we have a lot of fossils that come from areas where DNA doesn't preserve well, for example. And they may be candidates for this ghost population. So for example, the Pingo fossil from Taiwan that was actually dredged up in a fishing net, or Homo luzonensis from the Philippines. Some people have even looked to Homo floresiensis or Homo erectus as all sort of potential candidates for this genetic data or this ghost population. But I don't know that we've really identified it yet in the fossil record. The DNA that we think of as being from a ghost population is actually found in the genomic sequence of people who are living today, as well as in the genomic sequence from fossils, from the Neanderthal and Denisovan fossils. And I don't know if it's confusing to think about Denisovans as a ghost population, but I think at one time they were our ghost population that we've now identified.
Yeah.
So it's sort of a good comparison. Although now we know that throughout human evolution there are multiple ghost species. They've also been presumably there was a ghost species in Africa that is yet to be identified or named, but again, based on the DNA of living humans, there are genomic sequences that are best explained by a population that existed in the past that we haven't yet identified.
You've also helped pioneer an intriguing new tool, virtual archaeology, a way of teaching students how to excavate without their even having to leave the classroom. Now, this all began back in 2009. So how did this all come about?
So what I refer to as V-archaeology, this is sort of immersive virtual reality. And immersive virtual reality is a tool that I've been using to sort of simulate the field experience so that any student can try it without leaving the classroom. One of the problems that I have with our field work is that I can't take students with me into the field. Logistically, it's difficult, not just because of the distance and the amount of travel required to get from the States to Laos, but also Laos has very little infrastructure. So once you get in country, it's also very difficult to travel, and the accommodations are not necessarily the greatest. But Laos is still communist, and so that adds additional complexities with respect to bringing students. And this is really part of a bigger issue in training physical anthropologists and archaeologists. They need to be in the field to really learn field methods, but it's increasingly difficult to get students into the field. So we have this catch-22. And so what most students do is they go to a field school. But field schools are really financially and logistically impossible for most students. They simply can't afford them, or they can't afford to take the time during a summer break or a winter break to not work and to go to a field school. And so V-archaeology is a way for me to teach students archaeological field methods without leaving the classroom. So instead of going to a field site, I have created an entire fictional site and sort of a narrative around it that students explore using immersive virtual reality. And so when I say immersive virtual reality, what I mean by that is that students can perform actions, and in this case they're learning how to do things like survey and excavate and recover artifacts and all of the other things that we do in the field. And when they perform actions in VR, the environment responds to them. And so, for example, as they excavate and they are removing things with their virtual trowel, then the dirt actually is removed from the site. And if they are too rough with an artifact, then it breaks, and they have to deal with that. And they do all of this within a larger narrative, and so they're sort of the main character in an archaeological mystery that unfolds over the course of a semester. And in this way, I can both engage students, because it's a lot more fun to learn when you're sort of in your own video game, and I can teach students or prepare them to go to the field without them having to pay to go to a field school.
And this must have been pretty obvious how important this tech was during COVID.
It did. It became really obvious how I had been thinking about this from an accessibility standpoint, just making this field experience available to students. But during COVID, it really became obvious how a tool like this is important, because nobody could go to the field. And so something like this, it's not going to replace the field experience, but it is a nice substitution or a nice preparation for when we can't get into the field. So yeah, it became really obvious that tools like this were not only available, but they were really useful.
It sounds quite exciting. I mean, I'd like to try it myself, just have the fun of digging something up. But obviously, you can't use it for a real excavation, because you have to place what they're going to find into the simulation.
Right, and so I have created, just sort of for ease and for pedagogical reasons, I created a fictional site, and that was in part because I wanted to create this very engaging narrative around the site. And I had some very specific learning objectives, but in fact, if you wanted, then you could use photogrammetry, and you could use photography to go out and take a real site that exists, and you could create that in virtual reality, and then you could seed it just like it is in real life. So it is in fact possible to take a real site and then to create it, and then you can step inside of it with something like this. The idea for this I came up with several years ago, and then I worked with computer scientists here on campus to actually create the virtual environment. And then it has been supported by NSF in several iterations to create sort of this larger tool that has become not just an environment, but an actual class and an entire experience. And then I have a colleague in education, David Huang, who is a professor here as well, and he has come in to help out by really doing an analysis of the educational efficacy. And so he's come in to see, does this work? He's done an analysis or several analyses to look at whether or not this is a good learning tool, and to sort of quantify how this helps students learn and whether it helps students learn. And so we've sort of worked together, me as sort of a subject matter expert, working with engineers and computer scientists who have the programming expertise, and then like David as an educational expert who can look at sort of the validity and the success of the tool from an educational standpoint. And so we started just by sort of creating this as a class, and I've actually taught the class here on campus twice, and so I've run it twice, and it's been a great deal of fun. And we are currently working to sort of continue that idea of accessibility by making an effort and trying out some new ways to make virtual reality more accessible for students who have compromised mobility, in particular students who are in wheelchairs. This is an incredibly wheelchair-friendly campus, and we have a very large wheelchair population, in large part because of our wheelchair athletics. And so right now we're working on some ways to make virtual reality more accessible for students in wheelchairs, so that this class won't have any barriers to its accessibility. I don't want to create a class that introduces some of the barriers I'm trying to break down. I just wanted to add that right now I'm going through a period of revisions with this class, and sort of recreating some of the activities and making it a little more holistic and creating a better narrative and a better experience. So I've gotten a lot of feedback. I've gotten a lot of help from the students who have taken the class in the past. They constantly, were improving it by telling me what works and what doesn't. And so I am currently sort of revising a lot of the project. And once it's completely revised, then I will release it so that anybody who wants to use it is able to. It'll be available for anyone who wants it.
Yeah, sounds like an absolutely wonderful resource. You've been on some very exciting adventures over the years, but I'm sure there is much more to come. So, what projects are you working on that you can tell us about?
Yeah, so there's always more to do. Right now, we are working on a couple of things. And with respect to this particular tooth, with respect to the Denisovan tooth that we've been talking about, we're currently doing some analyses of growth and development. Since this is a child's tooth, it's a good opportunity to take a look at some of the questions of growth and development. Right now, we are assuming that sort of developmental standards are the same for Denisovans as they are for modern humans, but we want to take a look at that. Also hoping to do possibly some isotope analyses. Isotope analyses can help us to sort of understand the environment that this child was living in a little better. So we have a couple of analyses of this particular tooth that are ongoing. But more importantly, we want to get back in the field. We haven't been in the field since 2019. And so we are planning on our next field season for November and December of this year, 2022. And so we hope to get back in the field because, like I mentioned, there are just an enormous number of possibilities for places to excavate, and so there's lots of work to be done. And we can, when we go back, one of the things that we want to do is, we have focused in the past on these late Pleistocene, early modern human sites. But now we know that these middle Pleistocene breccia sites are really exciting and potentially really interesting. And we also know what to look for with respect to these sites. And so now when we go back, we might just need to change our focus a little bit. So we're looking at different kinds of sites with an eye on, potentially finding more Denisovans instead of just, focusing on the modern humans that we have been looking for in the past. So those are our big plans. And other than that, I fit that in between teaching anthropology and teaching anatomy.
And you never know when another ghost population might pop up somewhere.
You never know when a ghost population is going to pop up. It's true.
That'd make a good T-shirt. You never know when another ghost population is going to pop up. I will leave links to your research papers in the description below. And all that's left to say is thank you very much indeed for coming on to the show, Laura, and hopefully we can have you back on in the very near future.
Thanks, Mark, so much. I've enjoyed being here, and I appreciate the opportunity.